We built the most expensive telescope in human history to confirm what we thought we knew about the universe. It confirmed nothing. Instead, the James Webb Space Telescope pointed its mirror at the oldest light in existence and found galaxies that shouldn't be there. Massive, fully formed galaxies, blazing with stars, sitting in a part of the universe where our best models said almost nothing should exist yet. Not small proto-galaxies stumbling into existence. Not faint smudges of first light. Mature galaxies. Hundreds of them. Some with more stars than the Milky Way, and they were already old when the universe was still an infant. The math didn't just bend, it broke. And now one physicist is arguing that the only way to fix it is to accept something uncomfortable. That the universe isn't 13.8 billion years old. That it might be nearly twice that. 26.7 billion years. And if he's right, almost everything in your high school science textbook about the age of the cosmos is wrong. But if he's wrong, then we have a different problem. Because those galaxies are still there, and nobody can fully explain how they got so big, so fast. When NASA launched the James Webb Space Telescope on Christmas Day, 2021, the plan was straightforward. It was supposed to do what Hubble couldn't. See farther. See earlier. Peer back to the edge of time itself and watch the first galaxies flicker into existence. The telescope was designed for infrared. Light from the earliest objects in the universe has been stretched by 13 billion years of cosmic expansion, redshifted out of the visible spectrum entirely. Hubble could catch some of it. Webb was built to catch all of it. It sits 1.5 million kilometers from Earth, at a gravitational sweet spot called L2, where its tennis court-sized sunshield keeps the instruments colder than deep space itself. Minus 233 degrees Celsius. Cold enough for its detectors to pick up heat signatures from galaxies that formed when the universe was less than 500 million years old. The expectation was specific. At those distances, at those times, we should see small, messy clumps of gas, proto-galaxies. Irregular smears of first-generation stars just beginning the slow gravitational dance that would, over billions of years, build the spiral arms and galactic cores we recognize today. That's what every simulation predicted. That's what Lambda CDM, our standard model of cosmology, the model that accounts for dark matter, dark energy, and the expansion history of the universe, he told us we would find. Webb was supposed to confirm the timeline, fill in the details, put the final pieces of the puzzle together. Instead, it walked into the room and flipped the table. Almost immediately, the data started coming in wrong. Rohan Naidu, an astronomer at MIT, was at home when his algorithm flagged the first anomaly. A galaxy so far away that its light had been traveling for over 13 billion years. But it wasn't small. It wasn't faint. It was massive, bright, and structurally complex. It looked like it had been evolving for billions of years already. And yet, by our timeline, the universe had barely existed for 300 million years when this galaxy was already shining. He called his girlfriend over, told her it might be the most distant starlight anyone had ever seen. Then he started messaging colleagues, lots of exclamation marks. That was just the beginning. Within months, research teams across the world were pulling similar objects out of Webb's data. Not one or two anomalies. Hundreds. A team led by Joel Lager at Penn State identified 6 candidate galaxies from the first 500 to 700 million years of cosmic history that were so massive they started calling them universe breakers. One of them appeared to contain more stellar mass than 100 billion suns, at a time when our models said they shouldn't even exist yet. Lager didn't mince words. He said the discovery of massive galaxy formation that early in the universe upends what many of us had thought was settled science, and the data kept escalating. In January 2026, Webb confirmed its most distant galaxy yet, MOM-Z14, light from just 280 million years after the Big Bang. And MOM-Z14 wasn't alone. It was one of a growing population of unexpectedly bright galaxies in the early universe, 100 times more than theoretical models had predicted before Webb launched. The same month, a team at Texas A&M found something arguably stranger. Not just individual galaxies that were too big, too early, but a tightly packed collision of multiple galaxies, already merging and enriching the space around them with heavy elements like oxygen. At a time when most models said galaxy interactions should have been simple, if they were happening at all. Jacob Shen, a postdoctoral researcher at MIT, said there is a growing chasm between theory and observation related to the early universe. He's putting it politely. What Webb was showing was that the early universe was not the quiet, dark nursery we expected. It was a construction site already in full swing, building structures we thought took billions of years in a fraction of that time. So what do you do when the universe refuses to match your model? Most cosmologists started looking for astrophysical explanations. Maybe the galaxies aren't as massive as they appear. Maybe supermassive black holes at their centers are inflating the brightness, making them look heavier than they are. A team at the University of Texas found exactly that. Many of the so-called little red dots, the compact red point-like objects that caused the initial panic, turned out to have active black holes distorting their apparent mass. When you remove those from the analysis, the remaining early galaxies are not too massive to fit within predictions of the standard model, but not all of them. And that's where Rajendra Gupta comes in. Gupta is a theoretical physicist at the University of Ottawa. In 2023, he published a paper that went further than anyone else was willing to go. He argued that the impossible early galaxy problem isn't an astrophysics problem at all. It's a cosmology problem, and the only way to solve it is to accept that the universe is nearly twice as old as we think. His model combines two ideas. The first is the standard expanding universe, the Big Bang framework we already use. The second is a nearly century-old hypothesis called tired light, originally proposed by Fritz Zwicky in 1929. Tired light suggests that the redshift we observe in distant galaxies isn't caused entirely by the expansion of space. Part of it comes from photons losing energy as they travel across billions of light years, and the idea was largely abandoned decades ago because it conflicted with other observations, like the uniformity of the cosmic microwave background. But Gupta found a way to hybridize it. By combining tired light with the idea that fundamental physical constants, the coupling constants that govern how particles interact, might change over time, he produced a model that stretches the galaxy formation timeline by billions of years. His conclusion: the universe is 26.7 billion years old. At that age, the galaxies Webb is seeing aren't impossible at all. They've had plenty of time to form, merge, and mature. The impossible early galaxy problem simply disappears. But the mainstream response was swift and skeptical. Tamara Davis, a professor at the University of Queensland, pointed out that there are many measurements suggesting the universe is about 14 billion years old. The JWST calibration issues that initially inflated some galaxy distances have since been corrected. And the tired light hypothesis, even in hybrid form, still has problems with other observational data. So far, the scientific consensus hasn't moved. But Gupta's work did something important. It forced the question into the open. Not just, are these galaxies too big? But, is our entire timeline wrong? Here's the honest truth about where things stand. The universe breakers didn't break cosmology, at least not the way the headlines said they did. The standard model of cosmology, lambda CDM, is still standing. The Big Bang still happened. Dark matter and dark energy are still the best explanations for the large-scale structure and expansion of the universe. But something is off, even after you account for the little red dots, even after you correct for black hole contamination and recalibrate the instruments. There are still more bright, massive galaxies in the early universe than anyone predicted. Not 100 times more, maybe, but significantly more than zero. And the ones that remain are genuinely massive. They converted gas into stars at rates that our simulations can't replicate without changing the underlying physics. A study from UC Santa Cruz found that some of these early galaxies converted much more of their available gas into stars than current models allow. In the standard picture, only about 20% of gas in a primordial galaxy gets turned into stars. These galaxies appear to have blown past that limit, so either something accelerated star formation in the early universe, and something we haven't accounted for, or the timeline really is wrong. And there's another wrinkle: stars that seem too old for the universe they live in. The Methuselah star, HD 140283, has been measured at roughly 14.5 billion years old. The error bars bring it into uncomfortable proximity with the estimated age of the universe itself. If the universe is 13.8 billion years old, this star formed almost immediately after the Big Bang, which is possible, but unsettling. Then there's the Hubble tension. The expansion rate of the universe measured from the cosmic microwave background doesn't match the expansion rate measured from nearby supernovae. In December 2024, Webb confirmed this discrepancy. The universe is expanding faster than our models predict, and nobody knows why. These aren't isolated anomalies, they're pressure points, and each one, on its own, can probably be explained within the existing framework. Together, they form a pattern. The pattern of a model that works beautifully at large scales, but starts to crack when you push it to the edges. The most important sentence in modern cosmology might be this: it looks nothing like what we predicted. That's what Rohan Naidu said after confirming MOM-Z14. He said it plainly, without drama. And it's the most honest summary of where JWST has left us. We are not in a crisis. We're in something more uncomfortable than a crisis. We're in a transition. The old answers aren't wrong, exactly. They're incomplete. And the new data is arriving faster than new explanations. Most cosmologists still put their money on the standard model. Mike Boylan-Colchin at the University of Texas says the astrophysical explanations, faster star formation, earlier black holes, burstier galaxies, are probably sufficient to account for what Webb is seeing. The laws of physics don't need rewriting, they need fine-tuning. But fine-tuning is doing a lot of work in that sentence. Because what we're really saying is the universe did something in its first few 100 million years that we didn't predict, can't fully simulate, and are only now beginning to understand. Webb's successor observations are underway. Mid-infrared spectroscopy is revealing the chemical composition of these early galaxies, not just their brightness. The Nancy Grace Roman Space Telescope, scheduled to launch as early as late 2026, will survey enormous swaths of sky and boost the sample of early galaxies from hundreds into the thousands. Within a decade, astronomers predict, we'll know whether these galaxies are truly as massive as they appear and why. But here's the part that stays with you. We pointed the most powerful eye humanity has ever built at the beginning of time. We expected to see simplicity, darkness, giving way to faint, tentative light. The first nervous sparks of a young universe finding its footing. What we found was a universe already running, already building, already old. And the question isn't whether our models will survive. They probably will, in some form. The question is whether we're ready to accept that the universe was never as simple as we wanted it to be. That the story didn't start the way we wrote it. And that the beginning, whatever it looked like, was far more violent, far more productive, and far more mysterious than we had the imagination to predict. As the telescope showed us exactly what we asked to see, we just weren't prepared for the answer. If you want to go deeper into the discoveries that are reshaping everything we thought we knew, the video on screen right now covers another finding that has the scientific community arguing behind closed doors. Subscribe if you want to keep following this story. Because it's not over, Webb is still looking. And so far, every time it looks, we have to rewrite something.